Enjoying it. I felt like I should put a coat on this morning, actually. It's nice for a change. I will begin with the word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you guide our work today and help us to glorify you in what we do, Lord. In your name I pray. Amen. So I need to talk to you guys about the complex zeros, and then we'll break into groups and you guys work problems, okay? But in the other three sections, I spent like all of last Friday talking about what I'm about to talk about, okay? And so if you want to see more, just look at any of the Friday lectures for last week. But despite that, there were still a lot of students yesterday who were having trouble with the problems like this on the set of problems I'm about to let you guys work here after. So I'm going to break into groups in about 20 minutes or so, all right? So in the meantime, let's talk about this. Complex zeros. So your textbook is not helping, and the homework even less so, because it keeps, there's just some problems are on synthetic division, and if you watch the help me solve it and that sort of thing, then it's taking you away from my course and wasting your time, really. Because there's a theorem we can use where we don't have to do any of that synthetic division with complex numbers. There is a simpler way to do it. Let me show you, all right? So here's the theorem, which I'm going to keep coming back to for the next about 20 minutes or so. F of x, a polynomial, all right? And then alpha and beta, real numbers, with beta not equal to 0. If you don't like alpha and beta, you can make these a and b, whatever. Sad. All right, let's see here. Then, here's the deal. F of alpha plus I beta is equal to 0, if and only if. All right, that's interchangeable with the following. First of all, f of alpha minus I beta also being equal to 0. That's one thing you can say. All right, so the roots, complex zeros, have to come in conjugate pairs. And more than that, you have to have x minus alpha minus I beta and x minus alpha plus I beta factor of f of x, all right? So if those are zeros, then the factor theorem applied to this one and applied to that one give you these two factors in the factorization of the polynomial. Still, I've not gotten to the punchline. The thing that's really, really useful to us is what I'm about to write here, which is that when you multiply this out, all right, I'm just going to get straight to it, but just, there's like one algebra step I'm skipping here, but this multiplies out to alpha minus x minus alpha squared plus beta squared is factor of f of x. So what this means is if you have a complex zero, you get this corresponding prime factor. This is a prime factor, by the way, right? So that's all there is to it, all right? So like, for example, keep it real simple here. If I know that, f of x has f of, let's say, minus 2 plus 3i equal to 0. Yeah? Man, I'm just consistently off today. I'll get it eventually. Then, what does this tell us? This tells us then, what are consequences of that? Well, you have, first of all, you can count on this. Minus 2 minus 3i is also equal to 0. All right? What else can you count on? And x plus 2 squared plus 9 is factor of f of x. So I'm actually most interested in this result. All right? So some of the problems in your homework, they have things like, you know, let's say f of x equal to, well, I'm not going to talk about that today. What am I doing? My bad. I have an example for us, which is a little bit uglier. Let me put that down. Some of you are still catching up what I wrote. Give you a minute. All right, so here is one.
Is that supposed to be a D or an A?
A D or an A?
Like next to like the F, or like it kind of looks like a sausage.
Oh, that's an A?
Okay.
Yeah. All right, so here is an example. F of x equal to x to the power 5 minus 5x to the 4th minus 13x cubed minus 5x squared minus 14x, all right? So here is a fifth order polynomial, and I'm going to give us a hint. Try x equal to I. All right, so let's try evaluating this at x equals to I. Now, usually, plugging in the complex number is not something, I would not, if I was asking you to plug in 2 plus 3i or something, I wouldn't do that here, because I think, taking 2 plus 3i and raising it to the 5th power, that's not particularly interesting, and it would be like a lot of trouble for us. There's ones in your homeworks where they give you a quadratic formula and ask you to plug the complex number in and work it out, right? That's not too bad. You just plug it in and work it out. Since this is just I, this is pretty easy to evaluate. So let's try it. What's f of I? F of I is I to the power 5, right? Minus 5i to the 4th minus 13i cubed minus 5i squared minus 14i. How's that work out? Do you remember how these simplify? The key idea with powers of I was that I to the power 4, right? Well, I squared is minus 1, right? So I to the power I squared times I squared is minus 1 times minus 1, which is to say that I to the 4th power is just equal to 1. Right? I to the 4th is 1, I squared is minus 1. So that simplifies these down quite a bit. Like I to the 5th is just I to the 4th is just 1, so that's minus 5. I cubed, what's I cubed equal to?
1.
Not 1, but I cubed is equal to, if we multiply the I squared equals minus 1 by I, we get I cubed is equal to minus I. So I cubed is minus I. So that gives me minus 13 times minus I. I squared is minus 1, so that gives me a plus 5. And then minus 14i. How does this work out? What do we got? Look at it. We've got I plus 13i minus 14i. So we have 0 copies of I, right? And how many real numbers do we have? Minus 5 plus 5, right? Plus 0. So my point to you is, if you look at this and simplify, collect all like terms, real and imaginary, we get that f of I is equal to 0. All right? So going back to my theorem, so we can apply theorem with alpha equals to 0 and beta equals to 1. Right? If alpha equals to 0 and beta equals to 1, then alpha plus I beta is what? It's just equal to I, okay? That's what I want. I'm saying this is the case of alpha plus I beta equals to I. I've got my alpha equals to 0 and my beta equals to 1. So the theorem says what? X minus alpha quantity squared plus beta squared is a factor, which is just what here? That's just literally x squared plus 1 is factor. All right, x squared plus 1 is a factor. So then how do I factor out x squared plus 1 from this polynomial then? So if you watch the help me solve it and the read it's and all that stuff and you're in the MyLab and I told you don't do synthetic division, use long division, right? This is what I was talking about, specifically this stuff, because we don't actually need to do the square boxes with the complex numbers and all that. All we have to do is just do long division here, and let's do that. So to figure out how that factors out, I take my polynomial up here, x to the 5th minus 5x to the 4th minus 13x cubed minus 5x squared minus 14x, right? And I'm dividing x squared plus 1 into that. All right? How's that go? What do we start with? To get x to the power 5, what do I need to multiply x squared plus 1 by? I need a x cubed, right? X cubed times this gives me x to the 5th, plus x cubed. I'll write it over here just to, because that's kind of where it goes, right? So then you subtract these guys. What do we get? We get minus 5x to the 4th. Looks like minus 14x cubed minus 5x squared minus 14x. All right. Then how do I get that minus 5x to the 4th term to go away? Well, I need a minus 5 times my divisor. Minus 5 what? Not just minus 5, but minus 5 what? I need 5 times what to get me that? See it? Minus 5, I need an x squared here, yeah? Minus 5x squared times x squared gives me minus 5x to the 4th. And then I've got minus 5x squared. Take the difference. And we get, what do we get? We get minus 14x cubed. These guys cancel, which is super nice, minus 14x. So how do I get minus 14x cubed minus 14x? Well, I just subtract 14x, right, up here. So minus 14x. So that gives me minus 14x cubed minus 14x, and that's good because now we have a remainder of 0, right? So what does this long division tell me? This tells me that we can factor the given f of x as what? We have x squared plus 1, right? Times what? Times x cubed minus 5x squared minus 14x. Now, I'll give you guys a second here to catch up if you're lagging. I'd like to point out some features of this calculation. The only place we had to do any kind of complex numbers is what? And just in particular here in this example, just checking is actually x equals to I is 0 of the polynomial, right? After I know that it is, there's no complex arithmetic at all, right? The theorem does all of the work for you. The theorem tells you that x squared plus 1 is a factor, and then past that point, it's all real numbers, right? There's no like working with a box of complex numbers and a bunch of complex arithmetic steps. Yeah? Can we go further? Is this completely factored? I mean, x squared plus 1 is prime. We can't break that down without complex numbers, right? How does, can you guys factor this right here? Does this factor? Surely we can pull an x out, right? I'll pull it out front. So we've got x squared plus 1 times x squared minus 5x minus 14. Can you factor that? Is what? 2 times 7, right? We want a minus, so we better put the minus on the 7 and the plus on the 2. And there we'll have it. At least over the reals we'll have it. So I think we can do x plus 2 times x minus 7, like that. Right? So this would be factored completely over the real numbers, right? What if we were allowed to use complex numbers? How would we factor f of x? We can do a little bit better. Over complex numbers, we can split the prime things, basically. In complex numbers, the theorem tells you every prime factor splits into a pair of conjugate factors like this. So the way it works in this example is that in the complex numbers, you can break this down further. This is x plus I times x minus I. So this would be how it factors over the complex numbers, right? So this is factored over C. Now, I don't usually ask you guys to factor over the complex numbers, but it is something that I should talk about at least just a little bit in here. So there it is. Yeah. Any questions? Yeah. How many pages are the I don't know how many pages the quiz is yet. I'm still debating, but other questions? Look, so like oftentimes in these kind of problems, you're not even asked to evaluate at I, right? There's a whole bunch of problems where you're just given that the function is 0 on a complex number, right? So there's no complex arithmetic at all. All you have to do is use the theorem. Let's look at another example here. So so instead of giving us a hint this time, I'm just going to plain tell us that a particular complex number, when you evaluate it, it gives you 0. And this will give us a little bit more experience with long division here again. So this time we'll get x to the 5th minus 5x to the 4th plus 6x cubed minus 32x squared plus 136x plus 180. And we're going to be given that f of, let's see here, there it is. F of 4 plus I root 2 is equal to 0, and f of minus 1 plus 3i is equal to 0. All right, and then the question is to factor f of x completely, okay? Factor f of x completely over the reals. All right. So how are we going to go about that? So what is yeah? Oh no, I thought my eyes played tricks on me. I thought you raised your hand. So what does this f of 4 plus I root 2 tell you? If that's 0, what does that mean about you know, this right here. So if you look at this, this gives you the alpha is 4, right? The beta is what? Square root of 2. So that together gives me a factor of x minus 4 squared, right? Plus the square root of 2 squared. It's in our best interest to like FOIL that out and make it prettier for what follows, because we're going to want to long divide this into the quintic, okay? So this is going to give me x to the x squared minus 8x plus 16 plus 2, all right? Which we can simplify to what? X squared minus 8x plus 18, right? So this is one of the factors of f of x, right? It's a prime factor. What else? Well, we also know that f of minus 1 plus 3i is equal to 0, right? That was given to us. So if we look at this, how does the theorem play out here? What's our choice of alpha? What's our choice of beta? So this one has alpha equal to -1, beta equal to, yeah, the I, just the 3, yeah. So the beta is just like a real number. It's whatever multiplies the I. So, and then, so this is going to give us what? X minus a minus 1, which is x plus 1 squared, plus 3 squared, right? Multiply that out. What do we have? We have x squared plus 2x plus 1 plus 9, right? In other words, we have a factor of x squared plus 2x plus 10. All right. All right, so let me summarize what's going on here. We know two factors of this fifth order polynomial, right? We know two factors. And what do I mean by, what is a factor? What does that actually mean, right? That means that I can come up here, right? And I can write that thing is actually equal to what? It's equal to, you know, x squared minus 8x plus 18 times x squared plus 2x plus 10, right? Times something. Now, how do you find that something? I think long division's the way to go here, all right? Now, so you got two options, right? We can either do long division by the first factor, right? And then do another long division by the second factor, but I think that's not the best way to go here. An easier way to do it is to multiply those two factors out and just divide by the product of them, right? So if we multiply these, then we can just divide by that. Right, so how do you multiply those? I'll do it down here, okay? So x squared minus 8x plus 18 times x squared plus 2x plus 10. So when I'm multiplying two trinomials, how many different terms do you expect from that? 3 things times 3 things. When you multiply it out, you get 9 terms, right? Maybe we're not as familiar with this kind of foiling, so to speak, right? I should put quotes on that. It's not really foiling, right? There's not just a first, outer, inner, last. There's more, right? So the way I do this is I just use the distributive property, all right? So like I first do x squared times the second thing. So x squared times that gives me x to the 4th plus 2x cubed plus 10x squared. That's from multiplying the x squared, all right? Then I'll do the minus 8x. That gives me, you know, minus 8x cubed minus 16x squared minus 80x. All right? And then I'll do the 18 times that, right? So 18 times that gives me an 18x squared. And plus 36x plus 180. Yowzers. Right? Now all of these add together, and we don't have 9 terms in the end, right? We collect like terms. The way I've written it, I've stacked them so that you can see how they combine, right? So what you got is you got yourself an x to the 4th minus 6x cubed, 18, that's plus 12x squared. What's 36? What's minus 80 plus 36 is what? I think that's a minus 44. Plus 180. So that was a question? No? Oh, the top hat's not working? See, I was talking to my other section. Next semester, what I'm going to do, day 1, I'm going to open up top hat, and we're just going to top hat 27 times. And then we'll be done with it for the whole semester. Right? Just get it all done day 1, and then that way it won't be a continual like distraction to you guys, which is unfortunate. So I don't know why it's doing that. There has been issues yesterday also. Like sometimes people get on their phone, but they couldn't get on their computer. Other people can't get on their computer, but they can get on their phone. I never know what to tell you guys, except that the one thing I'm convinced of is that top hat's a waste of our time. That much I'm sure of. Of course, I have no control over this, you know. I haven't done anything different, like my computer's not off or anything. I don't, I don't know. Are you okay now? Yeah. So listen, as far as the top hat goes, if you have 3 or more like positive top hats since like last test, I'm not going to take points off your attendance, okay? So like don't stress about it, okay? Do come to class. Like coming to class is in your best interest, right? But anyway, okay, so that's a factor. If that's a factor, how do you factor that out of that? Long division, right? And the long division here, it looks scary, but it's actually really simple in the sense that there's not many steps. You just write down the polynomial we're dividing into, which is x to the 5th minus 5x to the 4th, plus 6x cubed minus 32x squared, plus 136x plus 180, right? And we're dividing what into that? X to the power 4 minus 6x cubed plus 12x squared minus 44x plus 180. I almost didn't leave myself enough room to write it. So how do you start? I mean, it's kind of like, how do you get x to the 5th from all that? What? We just put an x there, right? So you just put x here, and then x times this gives you what? Gives you x to the 5th minus 6x to the 4th plus 12x cubed minus 44x squared plus 180x. And then you subtract those. What does it leave us? So if we subtract those, what we get is we get x to the 4th. So 5 plus 6, minus 5 plus 6 is just 1, right? So I've got x to the 4th. Then I've got 6 minus 12, which is minus 6x cubed, right? And what's 32 plus, minus 32 plus 44? Well, I think that's 12 plus 12x squared. What's 100 and, oh, it's 136 minus 180 is what? I believe that's minus 44. And then, of course, plus 180. So then what happens? How do you get this from that? Wait a minute, this is that, right? See that? These are identical, which means that I should put a plus 1 up here, right? And then I get x to the 4th minus 6x cubed plus 12x squared minus 44x plus 180. And that leaves us a remainder of 0, which means that I can go up to the top, right? If you don't mind, I'm going to save myself a minute of writing here and just point out that now I can go and put that up here, right? The something is in fact x plus 1. And that is the polynomial completely factored. So the two quadratic factors out front, those are prime, they're never 0. What's the graph of this look like? What's the graph of y equals f of x look like? Do you guys know? What would the critical numbers here be?
Yep, 0 and 3.
0. And now where'd you get 0 from?
Oh, I don't know.
So to get a critical number, right? We either have to have division by 0 or the expression works out to 0, right? So if we look at this right here, this and that, those are both prime, right? Where are they coming from? They're coming from either this or this, right? Both of those are never 0 for any real number, because it's the sum of squares, one of which is for sure positive, yeah? The other which is for sure non-negative. So these first two terms can never be 0. Those don't give you critical numbers. And this gives us critical number what? -1. Right, so the number line here is very boring. It's got a single critical number of -1. There's just two cases. I mean, I know the function looks horrible, but it's actually very simple to graph. So it starts out plus over here. The x plus 1 is of odd power, so we flip signs. And so the graph, it just looks, oops, -1, my bad. Put my axis on the right side of -1, that'd probably be a good idea. So my x-intercept's there, and this thing essentially just looks like, I mean, kind of sort of like that. I mean, I'm not sure exactly the shape, but it passes through -1, that's about all I can tell you. I could tell you one other thing. What's the y-intercept of this graph? You guys tell me the y-intercept? What's that? 180, very good. It was not a trap. Like, that is a very, you know, I can give you just about any horrible formula I can think of and ask you to find the y-intercept for the graph. That's a very reasonable question. It does not require you to factor or any of the other stuff that we did here, right? So, you know, one of the students in one of the other sections was like, wait a minute, so this stuff here doesn't do anything to the graph? Right? This stuff at the beginning, these prime factors, what do they do to the graph? The answer is they do things to the graph which we don't have tools to really explain in this course, right? Like where exactly the inflection point is, and like where it's kind of like a little bit lumpy other places, that is going to be affected by those two terms. Like, you know, something interesting is going to happen with those two terms close to like x equals to 4 for this one and x equals to -1 for that one. But exactly the details of that is beyond our pay grade. There's only one kind of quadratic prime factor that we can graph properly, which is what? Like, if I give you, so here's a good question for the quiz. Graph y equals to, you know, 3 times x plus 1 squared plus, you know, 2. What is that? See, because there is a case of a prime, that's a prime quadratic, right? If you multiply this thing out, you've got, you know, well, let me not do it. Let me just say that this is a prime, right? There's no way you can factor that except to use complex numbers, okay? What's its graph? It's a what? What's that? A parabola, right. And where's the vertex? Not a trick question. You guys can do it.
-1 and 2.
-1 and 2 is the vertex, right? Very good. And so, listen, that is also what my alpha and, well, I shouldn't say that. The alpha will be the h part of the vertex. The beta is more complicated. Oh, yeah, I did that, didn't I? Thank you. -1 and 2. And what's the y-intercept? Let's see. What it's where? If I call this thing f of x, yeah. 2, 2, 3? 2, 2, and the y-intercept. Like I plugged 0 into the formula, right? So we have 3 times 0 plus 1 squared plus 2, which is 3 plus 2, right? Which is 5. Okay, now, so then what? We can graph it, right? So the vertex is at -1, 2, and it's got a y-intercept of about 5. It's symmetric about the vertex, right? So you can kind of see what it looks like from that. So, but as I was telling my other section as well, this is really the only case where you have a prime quadratic factor and we can in detail graph what it does. Okay, like the effect of the prime quadratic factor on more interesting examples like this, it's kind of above our pay grade. Anyway, that's all I got for you guys today in terms of this part of the lecture. So now I'm going to break you guys up into groups and let you play on these problems. And I'll turn off the camera here.